Hello students, in previous lecture I have discussed about the equivalence relation, a relation which is reflexive, symmetric and transitive. It's called as equivalence relation. Okay, so what is the equivalence relation? A relation tilde defined on set A is equivalence relation defined on set A if it is first reflexive, that is A is related to A for every A belongs to A. This is the other symbol for, okay, this is equivalent to A belongs to this tilde notation. Okay, second, this is equivalent to AA belongs to tilde. Symmetric, if AB belongs to R or A related to B in R, okay, implies B is related to A or any AB belongs to R. A. Whenever for given AB belongs to A is related to B, then B must be related to A. AB belongs to R implies BA belongs to R. Third, transitive, if for ABC belongs to A is related to B related to C implies A must be related to C. So if it is reflexive, symmetric, transitive, then it is known as equivalence relation. Equivalence relation is denoted by this symbol. Okay, so with help of this we are going to talk about equivalence class. Equivalence class. If tilde is equivalence relation on set A, A must be non-empty. Only on non-empty set you can talk about the equivalence relation. Then for A belongs to A, equivalence class of A is denoted by this symbol A bar, or some books are denoted by A. It is set of B belongs to A such that B is related to A. Set of those elements which are related to A. It is known as equivalence class. If I take the example now, let for P is equal to say x1, x2 and Q is equal to x2, y2, or say x1, y1 and x2, y2 in R2. P is related to Q if OP is equal to OQ. OP is equal to OQ. Distance of P, okay, distance of P from origin is equal to distance of Q from origin. Okay. Then show that tilde is equivalence relation on R2 describe equivalence classes. equivalence classes. This is our example set. So first one, reflexive. So I will take 3 points. Let PQR belongs to R2. Then first, for P belongs to R2, whatever arbitrary point, OP is equal to OP. Implies P is related to P. Distance of P from origin is same. OP is equal to OP. It is unique. And therefore, tilde is equivalence relation, reflexive relation on R2. If I take second, let PQ belongs to R2 be such that P is related to Q. What this implies by definition, therefore OP is equal to OQ. Therefore OQ is equal to OP. OP is equal to OQ means P and Q are at same distance from origin. P and Q are at same distance from origin. Is it clear? Okay. Third, let PQR belongs to R2 be such that it is not necessary to take that 3 points here. If you write that, then it is not necessary to write it here again. Such that P is related to Q and Q is related to R. What this implies is OP is equal to OQ and OQ is equal to OR. So P and Q are at same distance from origin, Q and R are at same distance from origin. As OQ is common distance here, this implies OP must be equal to OR. Which implies OP is equal to OR. Therefore, P is related to R. Okay. Sorry, here I forget to write. Okay. This implies P related to Q implies, therefore P implies Q is related to P, and therefore T lies symmetric relation on R2, right? So thus P related to Q, Q related to R implies P is related to R. Therefore tilde is transitive relation on XY plane or R2 set. This is your XY plane. Okay. From this, from 1, 2, 3, this relation tilde defined on A is equivalence relation on R2 or XY plane. Now we have to talk about what is the equivalence class. Equivalence class. So let P is equal to x1 y1 belongs to R. Case 1, if P is equal to origin, then equivalence class over is equal to set of all P belongs to equivalence. For P is equal to origin, equivalence, okay, let P belongs to R2. If P is origin, equivalence class of 0 bar is set of Q belongs to R2 such that OQ is equal to, or Q is related to O. This is equal to Q belongs to R2 such that OQ is equal to OO. But what is distance between OO? This distance is 0. Q belongs to R2 such that OQ must be equal to 0. Okay. Which implies Q is equal to, this is just singleton origin. Distance of origin from origin is 0. Okay. So equivalence class of origin, equivalence class of O is singleton 0. Right. Now if P belongs to R, 2 is the non-origin. Case 2, if P is equal to x1, y1 belongs to R2 is such that P is not equal to origin. Then equivalence class of P is P bar is equal to set of Q is equal to points xy such that OQ is equal to OP. Now OQ is equal to OP implies OQ square is equal to OP square. Therefore, what is OQ square now? Q is xy. X minus 0 square plus y minus 0 square is equal to OP square x1 minus 0 square plus y1 minus 0 square. Therefore, x square plus y square is equal to x1 square plus y1 square is equal to r square greater than 0. Fixed. And therefore, P bar is set of xy belongs to R2 such that x square plus y square is equal to x1 square plus y1 square. This is nothing but standard units. This is nothing but standard circle or circle with center origin and radius r is equal to under root of x square plus y square. Radius r is equal to under root of x1 square plus y1 square. Sorry. This is equivalence class of P. Equivalence class of P. So thus, any equivalence class under this relation, any equivalence class under this equivalence relation is circle with center origin, which is circle centered at origin. Centered at origin. Is it clear? Any equivalence class under this equivalence relation is circle centered at origin, whatever it may be, or singleton origin. Okay, which is nothing but 0. For other, it is a circle. For other, it is circle with positive radius. Circle with positive radius. Center is origin. Now you can observe what is your P bar. It is nothing but set of Q such that Q is equal to XY such that P is equal to OQ. So this is nothing but Q bar also. Equivalence class of Q bar is set of P such that OP is equal to OQ. OP is equal to OQ. Okay. So from this you can observe that equivalence class of any point on that circle. What is this circle? Is equivalence class P bar. Okay. So note equivalence class, if P bar is equivalence class and Q belongs to P bar, then P bar must be equal to Q bar. P bar must be equal to Q bar. That is our aim. Our aim is to prove that any two equivalence classes defined by that equivalence relations are either identical or disjoint. Okay. Moreover, we are going to prove that this equivalence class also contains P point. OP is equal to OP. OP is equal to OP. Right? Means P lies in equivalence class of P bar. Okay. P belongs to P bar. P belongs to P bar. Then Q belongs to P bar if and only if P bar is equal to Q bar. P bar is equal to Q bar. Now if I take our yesterday's example, if X is set of all students in our college and relation is defined to be two students X and Y are related if XY are studying in same class, then if I take a particular student from FYBSC, then his equivalence class contain all those students, those who are studying in his class. If I take equivalence class of other students from that same class, it is nothing but that class itself. If I choose particular student from SYBSC and if I take his equivalence class or her equivalence class, it is SYBSC class. If I take some student from MA, then his equivalence class is all students studying in MA class. And from this you can observe that any two equivalence classes are either identical or disjoint. Second one, every equivalence class contain representative of that class, means for X bar equivalence class, X lies in equivalence class of X bar. If Y lies in equivalence class of X, that is X bar, then equivalence class of X and Y, that is X bar and Y bar, must be equal. Very important result. We'll explain this in next lecture. Till that, bye bye. Thank you.